Hey everybody. So this video is going to be about equilibrium. Equilibrium is probably a word that you've heard before. When I think of equilibrium, I think of like having like a steady flow or a steady rhythm, like we're in equilibrium, like things are chilled, things are moving, things are okay. And at least for me, that's kind of what it means in a chemical reaction as well. So equilibrium, its like official definition, is a dynamic process. So dynamic means like ever moving and changing in which two opposing reactions, we'll talk more about that in a sec, so forward and reverse, are occurring at equal rates in a closed system. So breaking this down, like I said, dynamic is like ever changing, ever occurring. So like this is not stagnant, this is like active. Two opposing reactions, forward and reverse. So this is where we're gonna have kind of like maybe a moment. You know how in chemical reactions we write arrows, right? So we like write this. Okay, well, for a bunch of reactions, that's not really a thing. A lot of reactions actually are better written as a double arrow. And the double arrow infers that this reaction can both occur forward and reverse. Meaning, we can read the reaction this way, and we can also read the reaction this way. And what equilibrium is more specifically talking about is the fact that those reactions, the forward and the reverse, not only could they both happen, but they are both happening at the exact same time. Not only that, they're happening at the exact same time at an equal rate. And it's got to be a closed system, just because if it was open, then things can change it and ruin it. So I like these graphs, all right? So basically you do a chemical reaction, boom, something happens, okay? A and B, arbitrarily, it happens, okay? So that reaction starts happening and the reactants start getting used up. As reactants get used up, products get made, okay? So like, you know, if I'm making a grilled cheese sandwich, I start using up a lot of breaded cheese and I start making sandwiches, okay? And then over time, I have a certain amount of grilled cheese sandwiches and bread and cheese. The equal rates part, so this part's measuring rate, so that's the rate at which it is occurring. So obviously the forward reaction is happening exclusively at the beginning, and there therefore can be no reverse reaction. But as more and more of the forward can happen, more and more of the reverse can happen. And eventually they reach an equilibrium and mellow out, and they're both occurring at the same time, and therefore there's also no change in the amount of product and reactant that you have. So one more time, a dynamic process, ever changing, ever moving. Two opposing reactions, forward and reverse, occurring at the same rate in a closed system. Probably hard to imagine, probably hard to envision. Here is a real basic one for you. I would like you to imagine, you know what? Hang on just a second. Ta-da! A glass of water is at equilibrium. Let's think of our definition again. A dynamic process. Things are ever moving and ever changing. That is true. I'll tell you why in a moment. Two opposing reactions. The reaction that is taking place here is water evaporating and then recondensing. So two opposing reactions, so I'm going from liquid water to gaseous water. Happening at equal rates, meaning the amount of gaseous water and the amount of liquid water that I have at the current moment, they are both being produced at the same rate, so those current amounts are not changing. And it's a closed system because I put a plate on top. What? I'm going to take the plate off now because it's heavy. But please pretend that the plate is still on. Come back. All right. So, gaseous and liquid water. Okay, so here's kind of a better picture, maybe more at the molecular level. So when I initially poured water into the glass, there was just liquid water. And then as you know, some of that water evaporated. So some of the water molecules gained enough potential energy and became a gas. If this is a closed system, okay, those water molecules will eventually recondense and fall back down. They've got nowhere else to go. So eventually they'll lose some energy and they'll fall back down. But then some water molecules will gain energy. And this is going to be an ever-flowing, changing process. That's the dynamic part of it. So, equilibrium. Here is the very enthralling, exciting thing about equilibrium. When it is happening, to your eyeballs, you literally see nothing. There is no macroscopic change at equilibrium. Macro meaning big, macroscopic. So basically what you can see with your eyeballs. So what you can see with your eyeballs if something's at equilibrium is literally absolutely nothing. But it's dynamic, meaning it's constantly ever changing. You just can't see it. And the reason you can't see it is because it's happening at equal rates. And the concentrations of your reactants and your products is not changing over time. That was good timing. I was thirsty. So if I'm going to write out this equation of water evaporating and condensing, maybe a better way to write it out would be to go water, liquid, double arrow, water, gas. So that's where that double arrow comes into play. So basically the forward and the reverse reaction. So water vaporizing and evaporating, and then the water recondensing as such. So this would actually even happen if I started heating it. So if I had a hot plate and I started heating this, obviously more water would evaporate, right? So more water molecules would have the potential energy necessary, would have the potential energy necessary to then vaporize. But, and the key thing here is if this was a closed system, as more of the water is evaporating as it's heating up, more water is going to condense simultaneously. So that's the point of equilibrium, equal rates and no macroscopic change. So once a reaction is at equilibrium, something that we can then use to talk about that equilibrium is something called the equilibrium constant. That stands with the variable K. The equilibrium constant is basically a way to communicate, once it's at equilibrium, kind of what's going on. Or another way to say that is what's favored reactants or products. So for example, I drink a lot of water. Remember when this is fuller, okay, when this is at equilibrium in the closed system? One of the things that was currently favored at that moment was the liquid water, simply because there was more of it. But that's kind of two solid phases, right? The solid and the liquid and the gas, so that was maybe a lot easier to visualize. Sometimes when you've got an equation at equilibrium, it's really hard to tell what's favored. So the equilibrium constant is a way to measure that. So it is a calculation, and the equation for it is this. It's essentially products over reactants. So if you look, I've got like my base equation up here at the top, right? So like the A plus B equals C and D. These small letters in front are representing any potential coefficients, so any potential like large numbers from balancing in front. And then the capital letters A, B, C, and D are actually standing for the actual reactants and products, whatever they may be. So what you do here is you take the concentration and specifically the molarity of these reactants and products. And actually something we haven't talked about yet is a very common way in order to communicate concentration sometimes, rather than writing the number in moles per liter, is simply to put it in brackets. So if you see a number in brackets, that is also communicating the concentration and the molarity of that particular substance, so the moles per liter of that substance. So you take the concentration of your products, and then what you're going to do is you're going to put them to the power of whatever exponent is present, if there is one. So for example, if the exponent of C was a 2, you would take the concentration of C and you would square it down here. And then you would do the same thing with the reactants at the bottom. So products over reactants. One thing I want to be clear with is if you're measuring specifically the concentration, so specifically the molarity, we only measure molarity with solutions, right? So the moles per liter of a particular solution. So you're only allowed to calculate molarity of solutions. Well, only certain things can be solutions, right? Specifically things that are aqueous, and also gases can be solutions too. So if you've got a mixture of gases, for example, you can measure the moles per liter. So the moles per liter of all the gases present. And then obviously aqueous solutions are solutions, right? Your solute per your solvent. So you can only calculate K using aqueous and gaseous solutions because we are using the concentration and the molarity of these solutions to calculate K. So this is something we're going to talk more in depth later, but I'm just going to drop the line right now. Basically, once you are at equilibrium, very few things can actually affect the equilibrium. So for example, if you change the concentration of one of your reactants or products, okay, so like you dump more of one of them in there, for example, equilibrium will actually fluctuate in order to maintain equilibrium. This is something called Le Chatelier, which we'll talk more about later. Essentially, if you invite a stress into the environment, the equilibrium will shift in order to compensate for that stretch. So by changing the concentration, removing, adding products, reactants, all of that, if you change the pressure of a gas, it'll shift. The only thing that can actually change the K value, the only thing that can actually shift and change equilibrium is temperature. So again, we'll talk more about that later. So essentially when you calculate K, when you calculate the equilibrium constant of a particular reaction, you're going to get a number. And once you have that number, what you can do is look at that number and help it to interpret what is favored. So these are very rough guidelines. I want to be clear about that. There's not like a hard scale on how this goes. Generally, if your K is larger than 10, so I want you to think like a big number, that means there's more products than reactants, which means products are favored. If you think about it, if K is products over reactants, if K is large, there must be more products than reactants. If K is small, so like less than 0.1, then there's more reactants than products. So reactants are then favored at equilibrium. And if K is around 1, and by around 1, I mean we're going to say like from 0.1 to 10 is going to be our rough barrier, essentially then nothing is favored. So the amount of reactants and products are fairly equivalent. So what we're going to do is we're going to practice writing some K expressions. We're not going to do any of the math, so I've already basically told you the answer, but we're going to write the actual K expression and what it would look like ahead of time. So our first reaction here is H2 plus I2 equals 2HI. So if you remember, our general equation is products over reactants. So I've got my gas here, which is a solution, so this will be a part of my equation. So I'm going to take the concentration of HI, notice I did my brackets, and since this has a 2 exponent, I'm going to square whatever that value would be. And then I'm going to divide that by my reactants, which are both gases. So my concentration of I2 times my concentration of H2. These are very difficult working conditions. So this would be my K expression. So basically, if you want to think about it, this is like your basic formula for this particular reaction. So then if you actually did it, you would actually measure the concentration of HI and I2 and H2, and then you would plug in the numbers and get an answer. So let's pretend we did that. We had some numbers we plugged in, and we got this for an answer, 55.6. So if our answer is 55.6, we can then ask ourselves which side is favored. This is a large number. It is greater than 10. So what is favored here is products, meaning this is at equilibrium, so equal rates going back and forth, but there are more products than reactants. So the product side is favored over the reactant side. Let's try another one. So we're going to write out another K expression. Again, remember the basic equation is products over reactants. So my product here is ammonia, and that is a gas, so it can be a solution. So my concentration of NH3, and I'm going to square that over my two reactants here. So the concentration of H2, and I'm going to cube that because of the 3, and then N2. So that's my basic equation. Let's say I plugged in. Now look, the number is very small, less than 0.1, so in this case, reactants are favored. Why don't you try the other two on your own and then check back in when you're ready. So you might have noticed that these two reactions are actually opposite of one another. And their K expressions and their results are kind of opposite of one another as well. One thing I really want to point out here is, did you notice that a solid was written with both of these? Okay, so since it is a solid, you can't measure the concentration, the moles per liter of it. That is why I did not include it in my K expression. Remember, you can only actually have aqueous or gaseous solutions involved. The number was really small, so I said reactants. And then for the next one, my number was really big, so I said products. If you think about it, this kind of makes sense. So magnesium hydroxide in water, right? So this is just a dissolving equation. It can be at equilibrium though, so you can go back and forth. Magnesium hydroxide is actually insoluble if you look at your solubility rules, which makes sense why reactants are favored, because so few of those ions will actually form in solution. So for this one, I want you to write the K expression like we've been doing, and then I actually gave you numbers. So write the K expression, then I actually want you to plug in the numbers and solve for K yourself and see what you get for an answer. All right, so I've got my K expression right here, products over reactants. I plugged in my values right here, and I got an answer of 3.93, which is in the middle, so that's why neither is favored in this case. Dog.